Hi everyone, welcome to this video here about what's called reciprocal trig functions. Excuse me if you hear me sneezing during this. I've still got my head cold here at the moment, so apologies about any sort of sniffles during this. Okay, what I've got recorded here, I've put straight into OneNote, at least the written part of it. So you can refer back to that in the section on trigonometry, this page called Reciprocal Trig Functions. So what we're going to have a look at here is a very quick, just going over what we did in class yesterday, and then we'll have a look at this idea of reciprocal trig functions and then some identities that can be proven from that. And then we'll have a look at a few examples of using those identities in a few questions. So on screen, as you can see, we've got this right angle triangle here. So just highlight a few things here. So what we've got here is this right angle triangle, and the three basic trig ratios, as they're called, sine, cosine, and tangent, these ones here. Okay, defined in terms of the sides of this right angle triangle as given here. And what we looked at in class today was the link between sine, cosine, and tangent. So if we take sine being b over c, opposite over hypotenuse, divided by the cosine, cosine being the adjacent, so a over c. If we divide those two fractions, okay, here, and then do a little bit of simple multiplying of fractions or dividing of fractions, multiplying by the reciprocal, we end up with b over a, which we can see from this is equal to the tangent. So this gives us our first identity, that the sine of an angle divided by the cosine of an angle is equal to the tangent of an angle. Excuse me, I might just blow my nose again. Apologies, gentlemen. Now, these are the normal trig ratios, as they're called. So what are the reciprocal ones? Well, the reciprocal ones, let's just make a heading for that. Okay, whether we call them trig functions or trig ratios doesn't matter in this case. They're simply the reciprocal of each of these ones. So 1 over the sine of an angle, that would be defined to be hypotenuse over opposite. So C over B. Now that is actually given a name. It is known as the cosecant ratio. So if we write it in full, it's cosecant of an angle. But that is actually abbreviated to cosec of the angle. 1 over cosine is another one of the reciprocal trig ratios. That would be defined to be the reciprocal of the cosine one. So it's going to be hypotenuse over adjacent. So that would be C over A. And that is known as the secant ratio. So spelled S-E-C-A-N-T. And that is abbreviated to sec of the angle. Okay, I'm just going to move this down a little bit. And we also have the reciprocal of the tangent ratio. So that, in the case of this right angle triangle here, would be equal to the adjacent over opposite. So A over B, and that is known as the cotangent ratio. Cotangent of our angle, and that is abbreviated to COT, cot of the angle. So these are known as the reciprocal trig ratios, cosecant, secant, and cotangent. Just apologies again, guys. Right, so back again. So some of the questions that you do have in your workbook on page, say, 27, simply asks you to evaluate some of those reciprocal trig ratios. So let's have a look at an example of evaluating. So I'll take a couple of those. Let's say question number 56. So that asks you to evaluate the cotan of 1.257. Okay, well, if you look at your calculator, you're not going to find a cotan button, but you do have a tangent one. So that is simply equal to 1 over the tangent of 1.257. So I'm just going to grab my calculator. So yes, this is equal then to, just from the calculator, 0.325 3dp. Okay, and if we take one where you're given an exact value, for example, let's take question number 60, evaluate the cosec of 4 pi over 5. Well, 4 pi over 5, yeah, there's nothing really special about that. I mean, I suppose we could try and see if we could use a special triangle of that or something, but really I think we can just see what this might be, perhaps in degrees, and then see if we can write it perhaps as a fraction of pi. We'll try that. So this will be for cosec. Remember, that is 1 over sine. So I'm going to go 1 over the sine of 4 pi over 5. Change my calculator to degrees mode. And let's take the sine, put it in brackets, 4 pi over 5. And that is, okay, not what I was expecting to get. Just a moment. Sorry guys, just have a look at this again. Realise I don't need to put the calculator in degrees mode. We're not taking the inverse sine or anything like that. So it's simply going to be just calculating this straight on the calculator. And yeah, if we were asked to get an exact value, we'd have to use some other means. And I think I'll go over with that with you at another time if it comes up. So let's just keep the calculator in radians mode. Okay, and just plug this straight in. So let's take the sine of 4 pi over 5 and then take 1 divided by that answer. That gives 1.701. Okay, so how do you evaluate those cotan, cosec, and secant values? Simply convert them into the equivalent tangent ones and plug that into your calculator. Okay, let's have a look now at this idea of what's on page 27 of your workbook, this relationship between trig functions and their reciprocals. So I'm just going to put a bit of work on the screen so we can refer to it. So I'm just going to pause this video and come back to it in a moment. Okay, so back here again. So to get these relationships between trig functions and their reciprocals, I'm going to go back to that triangle that we had at the top of the screen. And if we simply apply Pythagoras' theorem to that triangle with sides A, B, and C, we have that A squared plus B squared would equal C squared. Now, we also have above there that sine of the angle is defined to be B over C. Now, we can make B the subject of that. Let's multiply C on the other side here, so we get B is equal to C sine theta. And we do the same with the cosine definition. Cosine of the angle equals A over C, so A would equal C cosine theta. Now, if you substitute into Pythagoras' theorem here, these expressions for A and B, we get the following. So instead of A, we'll write C cosine theta. So C cosine theta. That's going to be all squared. Plus B squared, which will be C sine theta all squared, is equal to C squared, which is on the right hand side. Now, if we expand the brackets, now we simply have two things being multiplied and the side here being squared, so this will be equal to C squared and the cosine of theta squared. Now, we write that as cos squared theta. So just over on the right hand side here, if we have cosine of an angle times itself, perfectly okay to write that as cos of the angle all squared. Be careful about writing it as cosine of the angle squared like that, because that looks like it's the cosine of theta squared, where the theta part is being squared. So this is correct here. I would not write it like that. Now, the shorthand for this, mathematicians write that as cos squared theta, and it means this. These two are equivalent. And this is the normal convention way of writing it. Okay, so that's what I'm going to use. So plus, and then this part is C squared sine squared theta equals C squared. Now you might notice that C squared is a common factor throughout this. So we can divide every term here by C squared. And then what we end up with is the C squareds cancelling all over the place. Now on the right hand side, remember C squared divided by itself is 1. That's also true obviously here as well. So what we end up with is cos squared of an angle plus sine squared of an angle. And the way that you will usually see that on formula sheet is actually with the sine squared first. So I'm going to write that as well. And then plus cos squared. Of course, the order of these two doesn't matter, so it doesn't matter if we have sine squared theta first, plus cos squared theta, and equal to, on the right-hand side, 1. So this is the second of our identities. Okay, this is known as a Pythagorean identity because it comes from Pythagoras' theorem. Okay, we've got a couple more to prove. There are 3 of those that we want to get, and we've got the first... No, we've got 3 still to get. No, we've got actually 2 still to get. Okay, so how do we get those other 2? So what we're going to do is we're going to take this expression here and we're simply going to divide through by cos squared. Okay, so let's get the second identity. I'll just swap to a different color here. So if we take our identity we've just proven and we divide everything through by cos squared. That's a bit messy. Let's tidy that up. Oh, come on, eraser. There we go. And on the right hand side, 1 over cos squared theta. All right, so what can we do with that? Well, hopefully you realize that cos squared theta divided by itself is a 1. Now, what about this here? Well, if we have a squared over b squared, hope you realize that's a over b all squared. So that would be true here. We've got sine theta over cos theta, and we can write that in that form. And we can also do that on the right hand side here, 1 over cos theta all squared. 1 times 1 would be 1, which is the 1 on top, and cos theta times itself is cos squared theta on the bottom. All right, now we've seen that 1 over cos theta, well, that's defined to be secant. So this is sec of theta all squared. We've got a plus 1 here, and we've seen before that sine over cosine is tangent. So that is tan of the angle all squared. And this is usually written as tan squared theta plus 1 equals sec squared theta. That's the second of our identities, second Pythagorean identity. One more to go. Let's swap to a different color again. All right, so number 3. Listen again for a moment. Okay, back again, guys. So if we take our first identity, and this time divide through by sine squared theta instead of cos squared, all right, let's do the same thing as we did above, but with this dividing through by sine squared instead. So this sine squared theta divided by itself would be a 1. Cos theta over sine theta all squared, and 1 over sine theta all squared. Now, this cos over sine. Well, we know that sine theta over cos theta is defined to be tan theta, what's equal to that. We've proven that above. Sine theta over cos theta, and this thing over here, this cos theta over sine theta on the left-hand side here, well, that is the reciprocal of this thing here. So 1 over that would equal 1 over tan. So the reciprocal of sine over cosine gives cosine theta over sine theta, and the 1 over tan theta that we've got on the right, well, 1 over tan is defined to be cotan. So what can we do? We can say there 1 there, and this now from our work over here, we can say, well, that's cotan theta all squared, and 1 over sine, that's defined to be cosec, so it's cosec theta all squared. And we'll just move down a little bit. Okay, how do we write that? 1 plus cot squared theta equals cosec squared theta. Okay, third of our Pythagorean identities. Okay, what we'll have a look at is a few examples now of what you're asked to do in the text here, which is do a few proofs. So if you have a look on page 28 and 29, I'm going to go through a couple, in fact 3 examples of using this work here to do this stuff where they say prove the following identities. Okay, so let's move this down and let's do a few examples. Okay, let's take a relatively simple one to start. Let's take question number 62. Right, so what you're asked to do is you're given this expression, the cotan of x, where x is just an angle, times the sine of an angle. You're asked to prove that that is equal to the cosine of an angle, the same angle. Now, with this kind of proof, how would you do that? How do you start off? Well, what we're going to try and do is we're going to take one of the sides, and we're usually going to take the side that looks more complicated. So on this example here, this left-hand side looks more complicated. It's got 2 things multiplied, and we've only got 1 thing on the right. So what we're going to do is we're going to take this left-hand side, and LHS is short for left-hand side. So what we're going to do is we're going to take the left-hand side, we're going to manipulate it, and see if we can get the right-hand side. When we do, we're finished. So the left-hand side, what can I do with that? Well, the only thing I can think of is to replace cotan with 1 over tangent. So the left-hand side would equal 1 over tangent times sine still. Now don't put equals cos here. What we want to do is we want to take this left-hand side, manipulate it, and end up with cosine. So the next line down would be, well, what can we do with that? Well, 1 over tangent, no point putting it back as cotan, we're just going around a circle there. But we also know that tangent is sine over cosine. And 1 over that would be the reciprocal of that. So just a reminder, sine x over cos x would equal tan x. So 1 over tan x would be the reciprocal of this left-hand side, cos x over sine x here. So I'm going to replace that 1 over tan with that, cos x over sine x times the sine x. We're just carrying that down. Now, hopefully you can see where we're going now. This and this will cancel. We'll multiply them together. Okay, just cancelling common factor there. And we're left with cos x, which is what we're trying to prove, which is equal to the right-hand side. So we take one of the sides and we want to get the other side. Okay, so that's one example. Let's take a look at another one. So I'm going to take here question number 65. Okay, so if we look at this cos squared x minus sine squared x equals 2 cos squared x minus 1. Well, both sides there look pretty complicated. But, so which side would we take? Well, I'm going to take the left-hand side again because I'm remembering that sine squared of an angle plus cos squared of an angle equals 1. And I could replace that sine squared x, this thing here, with 1 minus cos squared x then. So I'm going to use this identity here. And why would I do that? Because if I replace sine squared x, which would equal 1 minus cos squared x, I can see that on the right-hand side I've only got cosine. I've got a cos squared x and a 1. So that looks like it's a way I can take the left-hand side and end up with the right-hand side. So let's see if that actually works out. So leaving the cos squared x minus, in a bracket, 1 minus cos squared x. So this is the left-hand side. Please use this notation. Start with whichever side, like the left-hand one, and indicate that. So LHS equal to. Now, what is that equal to? Well, if I multiply out that bracket, put the negative through the bracket, it becomes minus 1 here, and plus cos squared x. And the 2 cos squared x becomes 2 lots of cos squared x. And I've got a minus 1, and that is the right-hand side. Okay, let's take one more example here. All right, so let's have a look at question number 77. So if you look at that one where you've got 1 divided by 1 plus sine x on the left, also plus 1 over 1 minus sine x on the left together, and we're meant to prove that that is equal to 2 sec squared x. Well, the left-hand side is definitely more complicated looking than the right. Now, what do I do if I've got two fractions? Well, the only thing I can think of from that is to basically add them together. So I need a common denominator. So if I look for a common denominator, it's the two denominators multiplied together. So, yeah, I'm actually going to just write that. I think I'll write that just as 1 plus sine x for a moment in bracket and 1 minus sine x. In a moment, we'll need to multiply that out. So what happens on top? Well, the left-hand fraction, I multiplied the bottom by 1 minus sine x, so I need to do the same for the top. So 1 times that 1 minus sine x is just 1 minus sine x. And if I do the same on the right-hand fraction, I've multiplied the bottom part by 1 plus sine x. If I do the same on the top, I get 1 times 1 plus sine x, which is going to be 1 plus sine x. So this again was the left-hand side. Okay, now on top, hopefully you can see that these will cancel. Okay, and leaving 2 on top. And what have we got on the bottom? Well, if you multiply out that, you get 1 times 1, 1 minus sine x plus sine x, and sine x times negative sine x is 1 minus sine squared x. The sines cancel, and we've got 1 minus sine squared x on the bottom. So again, this identity is going to be needed, because 1 minus sine squared x is equal to cos squared x. So we've got 2 over cos squared x. And remember that 1 over cosine is equal to sec x. So 1 over cos x squared is equal to sec squared x. So we've got a 2 on top. Basically, it can be thought of as like this. You don't have to write that, but you have to be able to see that that is true. And so that 1 over cos squared x, this part here, okay, can be replaced with over here sec squared x. So we've got 2 times sec squared x, which is that right hand side. So again, this last step, okay, this here can be thought of as 2 times 1 over cos squared x, and this here, hopefully you can see that because 1 over cos x is equal to sec x, so 1 over cos squared x, we're simply squaring both sides here, that is equal to sec squared x. So I'm replacing here this 1 over cos squared x with sec squared x. And we've also added 2 times that, so 2 sec squared x, which is the right hand side. Okay, all right, folks. Have a go at the questions now on those 4 pages. There are a few questions back on page 27 to do. Okay, and then the questions on pages 28, 29, and 30. They will need to be done by next Monday. Remember, with listing day, I don't see you tomorrow. I would try, if I was you, to get as much of that done tonight. Okay, so I can get it out of the way and then finish it off over the weekend, and we'll see you Monday. So again, it was the questions on page 28, 29, 30, and also 27. So pages 27, 28, 29, and 30. Okay, so enjoy. Okay, folks, we'll catch you tomorrow at Listing Day.